What if everything you thought you knew about the universe was wrong? We're used to thinking of space as an infinite, ever-expanding void, stretching endlessly in all directions. But what if the universe isn't infinite? What if it has a shape? Could we be living inside a cosmic loop, where traveling far enough in one direction might bring you right back to where you started? For centuries, scientists and philosophers have debated the true nature of the cosmos. Is space truly flat, or could it be curved in ways we struggle to comprehend? Could the universe be shaped like a giant torus, a multi-connected dodecahedron, or something even weirder? Modern physics gives us tools, like cosmic microwave background radiation, baryon acoustic oscillations, and topology, to probe these questions. But even with all our knowledge, the universe might be hiding its true form from us. Cosmic topology, unraveling the multidimensional puzzle. The universe is vast, but its shape and structure remain one of the greatest mysteries in modern science. While we often imagine space as an endless open expanse, the true nature of the cosmos could be far more complex. The field of cosmic topology seeks to answer a fundamental question: what is the shape of the universe? At first glance, the universe appears boundless, stretching infinitely in all directions. But what if this is just an illusion? Some scientists believe that space could be finite, yet unbounded, much like the surface of a sphere. A traveler on Earth, for example, can walk in a straight line forever and eventually return to the starting point without ever reaching an edge. If the universe works the same way on a grander scale, it could mean that space is wrapped around itself in ways that are hard to visualize. Mathematics provides the key to unlocking this puzzle. At its core, topology is the study of shapes and how they can be deformed, stretched, or connected. Unlike geometry, which focuses on precise angles and distances, topology is concerned with how a shape remains fundamentally the same, even if it undergoes continuous changes. This branch of mathematics is essential for understanding the possible structures of the universe. One of the simplest ways to think about cosmic topology is to imagine a two-dimensional world on a flat piece of paper. If you fold the paper into a cylinder, a creature living on this surface would see a continuous, wraparound space in one direction. If you connect both ends of the cylinder, forming a torus or donut shape, the creature would experience a repeating, looping universe. Scientists propose that the three-dimensional space we live in could behave in a similar way, with space curving back on itself in ways we cannot directly see. To determine the universe's topology, researchers rely on observations of the cosmic microwave background, or CMB, faint radiation left over from the Big Bang. This radiation carries subtle patterns that could reveal whether the universe has a complex shape. If light from distant galaxies follows paths that curve and connect, it could create mirages, repeated images of the same celestial structures appearing across the sky. Scientists have searched for these patterns, but the results remain inconclusive. Mathematical models offer several possibilities. The universe could be a simple, infinite expanse, stretching without end. It could be a finite yet boundless shape, where traveling far enough in one direction eventually brings you back to your starting point. It could also be a multi-connected space, where different paths through the cosmos loop in intricate ways. Some models suggest the universe might be a three-dimensional torus, a more complex shape like a twisted prism, or even something stranger, higher dimensional spaces beyond our everyday perception. The challenge of visualizing these shapes comes from the limitations of human perception. We exist in 3 dimensions, but our universe might be shaped by higher dimensional forces. Some theories propose that extra dimensions, hidden from direct observation, influence the fabric of space itself. These ideas stem from advanced mathematical frameworks, like string theory, which suggest that the universe may contain multiple hidden dimensions beyond length, width, and height. Einstein's theory of general relativity provides a foundation for understanding cosmic topology. It describes how space and time bend under the influence of gravity, creating the large-scale structure of the universe. According to relativity, space can be curved in different ways, positively like a sphere, negatively like a saddle, or flat like a sheet of paper. The universe's curvature, combined with its topology, determines how it expands and evolves over time. If the universe has a spherical shape, it means space is positively curved, much like the surface of a globe. This would imply a finite universe with no edges, where traveling in one direction eventually leads back to the starting point. If space is negatively curved, like a hyperbolic surface, the universe could have a more complex, saddle-like structure that creates unusual pathways for light and matter. A flat universe, the simplest possibility, would stretch infinitely in all directions without looping back on itself. Modern measurements suggest the universe is nearly flat, but this does not rule out exotic topologies. A flat space can still be connected in intricate ways, much like a video game world, where moving off one edge of the screen makes you reappear on the opposite side. Scientists use powerful telescopes and mathematical models to test whether our universe follows similar rules. In recent years, new observations have provided hints but no definitive answers. Some studies suggest patterns in cosmic radiation that might indicate a repeating structure, while others argue that these patterns can be explained by simpler models. The search continues as astronomers refine their tools and look deeper into the fabric of space. The three possible shapes of the universe. A flat universe is the simplest to imagine. In this model, space follows the rules of Euclidean geometry, the same kind of geometry used in everyday life. Parallel lines never meet, and the angles of a triangle always add up to 180 degrees. If the universe is truly flat, it means that space extends infinitely in all directions without bending back on itself. This would allow light to travel in straight paths without distortion, and objects would move along predictable, linear trajectories. A flat universe is also closely tied to the idea of an infinite cosmos. If space stretches forever without curving, then the universe could go on indefinitely. However, a flat universe does not have to be infinite. It could still be finite in volume if it has a complex topology that connects different regions of space in a looping or repeating manner. This would mean that while the universe appears infinite to an observer, it could actually be structured like a vast interconnected shape where traveling far enough in one direction might bring you back to your starting point. The second possibility is a spherical universe. In this model, space is positively curved. This means that straight lines eventually converge, and parallel lines will eventually meet. If the universe is spherical, it is finite in size but has no edges. Just like how an ant crawling on a globe never reaches a boundary, a traveler in a spherical universe could journey in any direction and eventually return to the starting point. A positively curved universe has interesting consequences for the way light moves. Light from distant galaxies could take multiple paths to reach us. This could create mirages of the same cosmic structures appearing in different parts of the sky. A spherical universe would also have a significant impact on its ultimate fate. If gravity dominates the expansion of the cosmos, a closed, curved universe could eventually stop expanding and begin to contract, leading to a collapse known as the Big Crunch. In this scenario, space would shrink over time until everything in existence is compressed into a single dense point, possibly leading to another cycle of expansion and collapse. The third possibility is a hyperbolic universe, where space is negatively curved like a saddle. In this model, straight lines diverge from each other, and the angles of a triangle add up to less than 180 degrees. A hyperbolic universe has an open structure, meaning it expands forever without curving back on itself. Unlike a spherical universe, a hyperbolic universe allows for an infinite number of possible paths through space. A hyperbolic universe would have a strange and counterintuitive geometry. The further 2 points are from each other, the more space stretches between them. This means that distances grow at an accelerating rate as objects move apart. Light traveling through a hyperbolic universe would follow curved paths, bending outward as it moves across space. This could create unusual visual effects. such as galaxies appearing larger than expected at extreme distances. One of the most fascinating aspects of a hyperbolic universe is its implications for cosmic expansion. If space has negative curvature, it could continue expanding at an ever-increasing rate, leading to a scenario where galaxies drift apart indefinitely. This is consistent with observations suggesting that the universe's expansion is accelerating, possibly driven by dark energy, the mysterious force that counteracts gravity and pushes space outward. To determine which of these three possibilities best describes reality, scientists rely on precise measurements of the CMB. Observations from satellites like WMAP and Planck have provided strong evidence that the universe is nearly flat, with only a tiny margin of uncertainty. However, the question is far from settled. Some theories suggest that space could be connected in ways we cannot directly observe, leading to hidden symmetries and repeating patterns across the cosmos. Others propose that the universe may have started with one shape and gradually evolved over time as cosmic expansion reshaped space itself. Challenging assumptions: why flat is only the beginning. Observations from the CMB, galaxy distributions, and large-scale structures suggest that space is incredibly close to being flat. But in science, assumptions are meant to be tested. The universe may not be as straightforward as it seems, and flatness could be just the beginning of a much deeper mystery. One of the reasons scientists believe the universe is flat is that it aligns with the simplest interpretation of Einstein's general relativity. But just because these principles describe our observations doesn't mean they capture the full picture. Observations of the CMB show temperature variations that suggest the universe is very close to flat. However, these measurements only apply to the observable universe, the region of space where light has had time to reach us since the beginning of cosmic expansion. The total universe could be much larger, and beyond our observational limits, space may curve in ways we have not yet detected. Even within the observable universe, small deviations from perfect flatness could exist. If the universe has a very slight curvature, it may take more sensitive measurements to detect it. A nearly flat universe might still have an intricate topology. One possibility is that the universe could be shaped like a three-dimensional torus. This would create an illusion of an infinite universe while actually being finite. The challenge in proving such a topology is that if the universe is large enough, the repeating patterns could be beyond our observable reach. Scientists have searched for signs of repeating cosmic structures, but so far no definitive evidence has been found. The assumption of flatness also depends on how the universe evolved over time. When we look at the early universe, we see a vastly different environment from today. The Big Bang was followed by a period of rapid expansion called inflation, which smoothed out irregularities in space-time. Inflationary models predict that this process drove the universe toward flatness, stretching out any initial curvature. But inflation itself is still not fully understood. If it worked differently than expected, it could mean the universe is not as flat as we think. Dark energy introduces another layer of complexity. While we don't yet know its true nature, its effects could influence the overall shape of the cosmos. Some theories suggest that as dark energy becomes more dominant over time, it could gradually curve space. If the influence of dark energy changes over billions of years, the shape of the universe itself could shift, moving from one state to another. Higher dimensions also challenge the assumption of a flat universe. String theory suggests that space-time could have multiple hidden dimensions curled up at microscopic scales. If these extra dimensions exist, they might subtly influence the way we measure curvature. A universe that appears flat on large scales might actually be embedded in a more complex, higher dimensional structure. Quantum mechanics raises even more questions. At the smallest scales, space is not smooth and continuous, but fluctuating and dynamic. This means that on the quantum level, the fabric of space-time itself could be constantly shifting, making the idea of a fixed shape meaningless. Some theories suggest that the universe underwent rapid transitions in shape in its earliest moments, meaning what we see today is only a temporary state in a much more complex system. Even if the universe is mostly flat, it might not be uniform. Some models propose a multi-connected cosmos, where different regions of space have different curvatures. In this scenario, the observable universe could be nearly flat, while larger, distant regions of the cosmos could have unexpected twists and folds. If true, this would mean that cosmic geometry is not an all-encompassing shape, but a more intricate and dynamic system shaped by energy, gravity, and space-time itself. Another alternative is that our universe is just one of many in a vast multiverse. If other universes exist beyond our own, they could have different shapes, curvatures, and physical laws. Some suggest that different regions of the multiverse could be connected, affecting the way space behaves at the largest scales. If true, the apparent flatness of our universe could be just a small part of a much larger, more complex reality. Scientists are constantly testing these ideas with better technology. Future missions will measure the CMB with even greater precision, looking for tiny distortions that could hint at hidden curvature. Advanced telescopes will map the large-scale structure of galaxies, searching for repeating patterns that could reveal the universe's topology. These efforts aim to answer one of the most fundamental questions in cosmology. Is the universe truly flat, or is it something far more intricate? Why a 3D universe can have a 4D shape. Our experience of the universe is three-dimensional. We move forward and backward, left and right, up and down. This seems natural because it is the way we interact with the world around us. But there is no rule that says the universe itself must be confined to three spatial dimensions. Some theories suggest that while we experience the universe in 3 dimensions, it could actually have a 4-dimensional shape that we cannot directly perceive. A simple way to imagine this concept is by thinking about shadows. A shadow is a 2-dimensional projection of a 3-dimensional object. If a sphere passes over a flat surface, its shadow appears as a changing circle. The 2-dimensional surface cannot fully capture the sphere's depth, only its cross-section at any given moment. If the universe itself exists within a higher dimensional space, then what we observe could be a 3-dimensional shadow of a more complex 4-dimensional shape. One of the most famous ways to think about this idea is through the concept of a hypersphere. A regular sphere has a 2-dimensional surface, but exists in 3-dimensional space. A hypersphere extends this idea by having a 3-dimensional surface that exists in 4-dimensional space. If the universe were shaped like a hypersphere, it would be finite, but without any boundaries. Traveling in one direction long enough would eventually bring you back to where you started, just like moving in a straight line on the surface of a sphere. A 4-dimensional space is difficult to picture because we are used to 3-dimensional thinking. But mathematics allows scientists to describe these shapes and their properties without needing a physical representation. In a hyperspherical universe, the rules of geometry would be slightly different from what we experience. Light traveling through space could curve in ways that make the universe appear flat in some measurements, while still having an underlying 4-dimensional shape. Another way to think about this idea is through a 3-dimensional torus. If space were structured this way in 4 dimensions, the universe could be connected in a way that loops back on itself. This could mean that distant galaxies might actually be duplicate images of closer ones, appearing multiple times from different perspectives. The idea of a 4-dimensional shape for the universe appears in real physics theories, particularly those that attempt to unify gravity with quantum mechanics. Some models suggest that space-time itself might be part of a larger structure, where additional dimensions influence how matter and energy behave. In string theory, the fundamental particles of the universe are not point-like, but tiny vibrating strings that move in a higher dimensional space. In some versions of these theories, our universe is a 3-dimensional brane floating in a higher dimensional space called the bulk. This would mean that while we can only move in 3 spatial dimensions, forces like gravity might extend into the extra dimension. Some models suggest that dark matter, the invisible substance that makes up most of the universe's mass, could be a sign of hidden dimensions. The presence of extra dimensions could also help explain some of the biggest mysteries in physics. For example, gravity is much weaker than the other fundamental forces, like electromagnetism. If gravity spreads into extra dimensions, it might seem weak to us simply because we are only experiencing a fraction of its true effect. This idea has led to experiments looking for tiny deviations in gravity's behavior at very small scales, which could hint at hidden dimensions. If space is part of a higher dimensional structure, then what we perceive as reality is only a limited slice of something much bigger. Just as a two-dimensional being living on a flat surface would struggle to understand the concept of depth, we may be unable to fully grasp the true nature of the cosmos. If higher dimensions exist, they might contain entire regions of space and time beyond anything we can currently observe. While the idea of a four-dimensional universe remains speculative, it provides a powerful way to rethink our place in the cosmos. The history of science has shown that reality is often more complex than it first appears. The discovery that Earth is not the center of the universe, that time and space are connected, and that quantum mechanics defies classical intuition all show that our understanding of reality continues to evolve. The possibility that our universe has a higher dimensional shape is another step in this journey, challenging us to see beyond what we can directly experience. The universe as a manifold. Concepts in non-Euclidean geometry. For most of human history, the assumption was that space followed the rules of Euclidean geometry. But as scientists explored the nature of the universe, they realized that space might not follow these simple rules. One of the most important ideas in modern physics is that space is not just an empty backdrop, but a dynamic structure that can bend and twist. This leads to the concept of the universe as a manifold. A manifold is a mathematical space that can be curved and distorted while still appearing locally flat. Just as the surface of the Earth looks flat to someone standing on it but curves on a larger scale, space itself might behave the same way. The idea that space can curve comes from non-Euclidean geometry, a field of mathematics that challenges traditional notions of shapes and distances. In Euclidean geometry, the shortest distance between 2 points is a straight line. But in non-Euclidean geometry, this is not always true. If space is curved, the shortest path between 2 points might follow a curved trajectory rather than a straight line. This is a key idea in Einstein's general theory of relativity, which describes how massive objects like stars and planets bend space-time around them. There are different ways that space can be curved, and each one creates a different kind of geometry. Manifolds provide a way to describe all these possibilities mathematically. A manifold can be curved without breaking or tearing. It allows physicists to model the universe as a shape that may be far more complex than we can visualize. Some manifolds are simple, like a sphere, while others are much more intricate, involving extra dimensions or connections between different regions of space. One of the key insights from non-Euclidean geometry is that space does not need to exist in a higher dimension to be curved. The surface of the Earth is two-dimensional, yet it curves within itself without requiring a third dimension to contain it. Similarly, space-time can bend and curve without needing a higher dimensional space to hold it. This idea is essential to general relativity, where gravity is not a force pulling objects together, but rather the curvature of space-time itself. If space is a complex manifold, it might be connected in unexpected ways. Some theories suggest that different parts of the universe could be linked by hidden shortcuts called wormholes. These would be tunnels through space-time that connect distant regions, allowing travel between them in ways that would be impossible in a purely Euclidean universe. While wormholes remain theoretical, they emerge naturally from the equations of general relativity when space is treated as a manifold. One of the challenges in studying cosmic topology is that we can only observe a limited part of the universe. Light has only had a finite amount of time to travel since the Big Bang, meaning that we can only see objects within a certain distance from us. If the universe is much larger than this observable region, then its true shape may be hidden beyond our reach. Non-Euclidean geometry also plays a role in modern theories of physics that go beyond general relativity. Some models of quantum gravity suggest that space-time itself might be a fluctuating, dynamic manifold rather than a smooth, continuous structure. If this is true, then the geometry of the universe could be shaped by quantum effects. Poincaré's dodecahedral space, a hidden blueprint of the cosmos. The search for the universe's shape has led to many fascinating possibilities, some simple and others incredibly complex. One of the most intriguing and mathematically rich proposals is the idea that the cosmos might be modeled by a dodecahedral structure, an idea first explored by the French mathematician Henri Poincaré. At the heart of this idea is the Poincaré dodecahedral space, a three-dimensional shape formed by connecting the faces of a dodecahedron, a polyhedron with 12 pentagonal faces. In this model, space is finite yet unbounded. If someone traveled far enough in one direction, they would eventually return to their starting point, much like in toroidal cosmology, but with a more complex path. Instead of space curving back in a simple loop, the dodecahedral universe twists and connects in a way that alters how distances and directions behave on the cosmic scale. The mathematical foundation of this model comes from non-Euclidean geometry. In a dodecahedral space, the angles and distances do not follow the simple rules of a cube or sphere, but instead are governed by hyperbolic and spherical properties. The way light moves in such a space is different from what one would expect in an infinite or traditionally curved universe. The same object might appear in multiple locations due to how space folds in on itself, meaning the night sky could contain repeated patterns of galaxies without us realizing it. This model gained serious attention in the early 2000s when researchers studied the CMB. If the universe were truly infinite, this radiation should display random fluctuations on all scales. However, some studies suggested that the largest scale fluctuations were unexpectedly small. One possible explanation was that the universe had a finite, multi-connected structure, meaning space wrapped around itself in a way that limited how large these fluctuations could be. The Poincaré dodecahedral model offers an explanation for this observed limitation. Because space in this model connects back onto itself in a dodecahedral pattern, it restricts how certain wavelengths of radiation can develop. If the universe truly follows this shape, then it would be smaller than an infinite, ever-expanding cosmos. Some studies have estimated that if the dodecahedral space is correct, the universe might be around 30 billion light-years in diameter, rather than infinite. If space wraps around in a dodecahedral shape, then certain regions of the sky should show matching temperature patterns, like puzzle pieces that fit together across vast cosmic distances. Scientists have searched for these matching patterns using satellite data from telescopes like WMAP and Planck, but so far the results have been inconclusive. Some studies have found hints of dodecahedral-like symmetries, while others argue that the data does not strongly support the idea. A multi-connected finite universe means that there are limits to how far space extends, but without any defined edges or boundaries. This idea also ties into theories about the fundamental nature of the cosmos, including how it may have formed in the moments after the Big Bang. Some models of early cosmic inflation suggest that space could naturally form multi-connected structures, meaning that a dodecahedral universe might arise from deep mathematical principles rather than being a coincidence. The dodecahedral model also challenges the way we think about infinity. If space is truly finite yet unbounded, then it forces a re-examination of what it means for something to be endless. Instead of stretching forever, the universe would be a vast but looping structure where movement in any direction would eventually lead back to familiar territory. This concept aligns with ancient philosophical ideas that the cosmos is both complete and continuous, rather than infinitely sprawling in all directions. Beyond its scientific implications, the idea of a dodecahedral universe has inspired connections between cosmology and geometry. The dodecahedron itself has been a symbol of mathematical beauty for centuries, dating back to Plato, who associated it with the heavens. The possibility that the universe follows this geometric structure adds a poetic layer to the study of cosmology, linking the shape of space to patterns found in nature and mathematics. Whether space is infinite, looped, toroidal, dodecahedral, or something even stranger is still unknown. Each model offers a different way to think about the cosmos, challenging assumptions and providing new ways to interpret the vastness of existence. As technology improves and our ability to observe the deepest parts of space advances, new clues may emerge that reveal whether the universe has a hidden geometric blueprint guiding its structure. Fractal patterns in space, the geometry of complexity. The universe appears vast and chaotic at first glance, but beneath its complexity, there may be hidden patterns that repeat at different scales. This idea is at the heart of fractal geometry, a branch of mathematics that studies shapes and structures that remain similar no matter how much they are magnified. In nature, fractals are seen in snowflakes, lightning bolts, tree branches, and even coastlines. Some scientists believe that similar fractal-like structures might be present on a cosmic scale, shaping the distribution of galaxies and matter throughout the universe. At smaller scales, fractals describe objects that display self-similarity, meaning that a small part of the object resembles the whole. A tree is a simple example. The pattern of its branches remains consistent whether you look at the whole tree or just a single branch. If this same principle applies to the structure of the universe, then galaxies and galaxy clusters might form patterns that echo across different scales, suggesting that the cosmos has a deeper underlying order. Astronomers have long studied the way galaxies are distributed throughout space, mapping their locations and looking for patterns. The standard model of cosmology suggests that matter in the universe is arranged in a web-like structure known as the cosmic web. This web consists of long, thin filaments of galaxies stretching across vast distances, separated by enormous empty spaces known as voids. When viewed on a large scale, the universe does not appear random, but rather as a network of interconnected filaments, much like the branching patterns of rivers or neural connections in the brain. Some researchers argue that this cosmic web might have a fractal structure, meaning that the arrangement of galaxies follows a repeating pattern at different levels of magnification. This would suggest that the same fundamental rules governing the formation of small-scale structures like dust clouds and star clusters also apply to much larger cosmic structures. This idea challenges the traditional view of cosmology, which assumes that at a certain scale, the universe becomes homogeneous and lacks structure. Studies of galaxy distributions have shown intriguing results. Some research suggests that galaxies do, in fact, exhibit fractal-like clustering up to a certain scale, meaning that their arrangement is not entirely uniform but follows a self-similar pattern. Other studies indicate that this effect weakens at the largest observable scales, where the universe does appear more evenly spread out. The debate over whether the universe has a true fractal structure remains unresolved, but the presence of large-scale clustering suggests that at least some level of fractal behavior is at play. One of the most well-known fractal structures in mathematics is the Mandelbrot set, a complex and infinitely detailed shape that reveals repeating patterns no matter how much it is zoomed in. Some scientists have speculated that the universe might follow a similar principle, where different levels of structure emerge depending on how closely they are examined. If the universe has a fractal-like distribution of matter, it might suggest that physical laws governing cosmic structure formation are deeply connected to mathematical principles found in fractal geometry. Fractal patterns have also been observed in other areas of astrophysics. Some models suggest that turbulence in interstellar gas clouds follows fractal rules, influencing how stars form. The arrangement of dark matter might also follow fractal-like structures, shaping the way galaxies come together over time. Even the CMB has been studied for signs of fractal patterns, though results remain inconclusive. If the universe is governed by fractal-like principles, it would mean that complexity and self-organization emerge naturally at all scales, rather than being confined to specific regions. This could challenge the way cosmologists model the evolution of the universe and provide new insights into how galaxies and large-scale structures form over billions of years. One of the challenges in studying fractal patterns in the universe is the limitation of observation. While computer simulations can help model large-scale cosmic structures, proving whether the universe truly follows a fractal design requires more precise data from deep space observations. Many fractals arise from simple mathematical formulas, yet they produce incredibly complex and beautiful structures. This suggests that the cosmos itself may be shaped by simple rules that generate complexity over time. The idea that the same mathematical patterns can describe objects as small as a fern leaf and as large as galaxy clusters points to a deep connection between the laws of physics and the mathematics of fractals. Curved spacetime, the intersection of geometry and general relativity. Space and time are not separate. They are part of a single fabric that bends and stretches under the influence of mass and energy. Instead of imagining space as a fixed, empty stage where objects move, general relativity describes it as a dynamic surface that curves in response to matter. This curvature determines how objects move, replacing the idea of gravity as a force with the concept of warped spacetime. To understand this, imagine placing a heavy ball on a stretched rubber sheet. The ball sinks into the fabric, creating a depression. If you then roll a smaller ball across the sheet, it doesn't travel in a straight line, but instead curves around the depression, following a path similar to how planets orbit stars. The heavier the object, the deeper the curve. In space, massive bodies like planets, stars, and black holes distort the space-time around them, guiding the motion of nearby objects. This warping effect is why the Moon stays in orbit around the Earth, and why light bends when it passes near massive galaxies. One of the most famous predictions of general relativity is time dilation, where time moves more slowly in stronger gravitational fields. This effect has been measured with incredible precision. Atomic clocks placed on Earth's surface, where gravity is stronger, tick slightly slower than those on satellites orbiting the planet. The difference is tiny but measurable, and modern GPS systems must correct for this effect to provide accurate location data. Light itself follows the curvature of space-time, bending when it passes near massive objects. This effect, known as gravitational lensing, has become a crucial tool for astronomers. When light from a distant galaxy travels towards Earth but passes near a massive cluster of galaxies, the cluster's gravity bends the light, distorting the image and sometimes even creating multiple copies of the same distant object. Observing these warped images allows scientists to study invisible matter, such as dark matter. The concept of curved spacetime also predicts the existence of black holes, regions of space where gravity is so intense that nothing, not even light, can escape. Black holes form when massive stars collapse, crushing their mass into an infinitely dense point known as a singularity. Around this singularity is the event horizon, the boundary beyond which nothing can return. The extreme curvature of space-time near a black hole warps time so severely that from an outside observer's perspective, anything falling in appears to slow down and never actually cross the horizon. The universe itself may be shaped by these same principles. Cosmologists use general relativity to describe the large-scale structure of the cosmos. The evidence so far suggests that space-time is nearly flat. These measurements help refine our models of the universe's evolution and its possible future. One of the most striking aspects of space-time curvature is its role in cosmic expansion. Observations of distant galaxies reveal that space is not just stretching, but accelerating outward due to dark energy. The discovery of this acceleration was unexpected and suggested that general relativity alone might not fully describe the behavior of the cosmos on the largest scales. Some theories propose modifications to Einstein's equations, while others explore the possibility that spacetime itself has additional dimensions that influence its expansion. Mathematical models describe spacetime as a manifold, a flexible surface that can bend and twist. Different models predict different behaviors. from oscillating universes that expand and contract in cycles to bubble-like regions of space-time that may be connected in higher dimensional ways. Studying the curvature of space-time has practical applications that affect daily life. The principles of general relativity ensure that satellites remain synchronized with Earth-based time, allowing navigation systems to function correctly. Spacecraft traveling to other planets must account for gravitational effects when plotting their trajectories. Even predicting the motion of objects near the Sun requires adjustments for space-time curvature, as light from distant stars bends slightly when passing through the Sun's gravitational field. While Einstein's theory has been tested repeatedly and confirmed through observations, there are still unanswered questions. The connection between general relativity and quantum mechanics remains one of the biggest challenges in modern physics. Space-time appears smooth and continuous at large scales, but at extremely small distances, quantum effects suggest that it may be granular or fluctuate unpredictably. Could the universe be a Klein bottle or a Mobius strip? Some of the strangest ideas in topology suggest that the universe could behave in exactly this way. A Mobius strip is one of the simplest examples. It is a surface with only one continuous side and one edge. If you take a strip of paper, twist it once, and glue the ends together, you create a Mobius strip. A small ant crawling along the surface would eventually return to its starting point, but mirrored. It would have traveled across both sides without ever crossing an edge. In this type of space, direction itself becomes distorted, challenging the idea that left and right are fixed concepts. The Mobius strip is just a two-dimensional surface embedded in three-dimensional space. But what if a similar property existed in 3 dimensions? A Klein bottle takes this idea further. In mathematical terms, it is a shape that has no true inside or outside. It loops back on itself in a way that cannot be fully visualized in 3 dimensions without intersecting, but in 4-dimensional space, it can exist as a smooth, continuous shape. If the universe had a structure similar to a Klein bottle, traveling far enough in one direction might bring you back to your starting point, but not in the same orientation. You might find yourself reversed, as if you had passed through a cosmic mirror. These concepts belong to the field of topology. In normal geometry, we rely on clear distinctions, inside and outside, left and right, up and down. But in topology, these distinctions can break down. A sphere remains a sphere even if it is stretched into an oval, just as a donut retains its essential shape, even if it is warped. But non-orientable surfaces like the Mobius strip and the Klein bottle challenge these assumptions by introducing a type of space where direction itself is relative. Could the entire universe have such a structure? Some physicists have explored the idea that space might be non-orientable on a cosmic scale. If so, then light traveling across the universe could eventually return transformed. This could create strange patterns in the sky, where distant galaxies appear mirrored or repeated in unexpected ways. If the universe was shaped like a Klein bottle or had a Mobius-like topology, then some regions of cosmic radiation might appear flipped or rotated relative to others. While no definitive evidence has been found, some unusual alignments in the data have led people to consider the universe's shape to perhaps be more complex than a simple infinite expanse. If space does have a Mobius or Klein bottle-like structure, it could have deep implications for physics. In quantum mechanics, particles behave as waves, spreading out through space in probabilistic patterns. If space itself is twisted or non-orientable, it could subtly influence how particles interact across vast distances. This could lead to new symmetries in the laws of physics, hidden connections between different parts of space that might explain some of the fundamental mysteries of the universe. At the smallest scales, space-time itself may have strange, twisted properties. The theory of quantum gravity suggests that space consists of tiny loops and folds. Some models propose that on these microscopic scales, space-time behaves like a network of interconnected Mobius strips or Klein bottles, forming a kind of quantum fabric that underlies all of reality. If this is true, then the non-orientable nature of space may not just be a large-scale phenomenon. It may be embedded in the very structure of the universe at every level. A universe with such a structure would also challenge how we think about travel and motion. These ideas have been explored in speculative physics, where some theories suggest that certain paths through space-time might allow for closed loops, potentially influencing concepts like time travel and causality. Mapping the invisible, baryon acoustic oscillations as cosmic rulers. Measuring distances in space is one of the biggest challenges in cosmology. Unlike everyday measurements on Earth, where rulers, measuring tapes, and laser-based tools provide direct and reliable readings, space presents a very different set of problems. There are no fixed points or absolute reference markers. Everything is moving. Galaxies drift apart, clusters shift over time, and the fabric of space itself expands. Astronomers must rely on indirect techniques to estimate the size and scale of the universe. Some of these methods include using the brightness of supernovae or the redshift of galaxies. However, one of the most precise and fascinating ways to measure cosmic distances is through baryon acoustic oscillations, or BAO, fossil-like imprints from the early universe that act as cosmic rulers. BAO are the result of sound waves that once traveled through the hot plasma of the early universe. To understand them, it helps to go back to a time before stars and galaxies existed, before light could even travel freely. In the first 380,000 years after the Big Bang, the universe was an incredibly dense and hot mixture of subatomic particles, mostly protons and electrons, along with a sea of photons. Because this plasma was so tightly packed, photons couldn't travel far without colliding with particles, and as a result, light could not escape. This period is often referred to as the photon-baryon fluid, where pressure waves moved through the hot, dense environment, much like ripples spreading through water. The key force at play was the interaction between gravity and radiation pressure. Gravity worked to pull matter together, forming regions of higher density. At the same time, radiation pressure from photons pushed outward, creating oscillations, expanding and contracting waves of matter in the primordial plasma. These oscillations were responsible for forming a repeating pattern, much like the crests and troughs of a sound wave. They moved outward from initial points of higher density, traveling at a fixed speed dictated by the physical conditions of the early universe. Then, something remarkable happened. As the universe expanded, it cooled. Eventually, temperatures dropped enough for protons and electrons to combine, forming neutral hydrogen atoms in a process called recombination. When this happened, photons were suddenly able to travel freely, escaping the dense fog of the early universe and forming what we now detect as the CMB. But at the same time, the pressure waves in the photon-baryon fluid froze in place. The outward traveling sound waves could no longer continue, leaving behind a snapshot of their last positions. The result of this process was a preferred scale in the distribution of matter. The oscillations left behind subtle variations in density, with regions of slightly higher matter concentration appearing at a fixed distance from the original points of perturbation. This meant that over cosmic time, as galaxies formed and clustered together, they retained an imprint of these primordial sound waves. Even today, billions of years later, galaxies are slightly more likely to be found separated by this specific scale, which is approximately 500 million light-years. This consistent spacing provides a natural standard ruler for measuring cosmic distances. Unlike individual galaxies, which vary in size and brightness, the BAO scale is determined by fundamental physics and remains unchanged over time. This makes it an incredibly powerful tool for cosmologists. By measuring how the BAO scale appears across different epochs in the universe's history, scientists can track how the cosmos has expanded and even determine its overall shape and structure. To detect BAO in the modern universe, astronomers conduct massive galaxy surveys. These surveys map the positions of millions of galaxies, looking for statistical patterns in their distribution. The Sloan Digital Sky Survey was one of the first major projects to observe BAO signals, followed by more advanced surveys, such as the Dark Energy Spectroscopic Instrument and the upcoming Euclid mission. These surveys carefully measure how galaxies are clustered, searching for the subtle excess in galaxy pairs that are separated by the BAO scale. One of the most important applications of BAO is in measuring dark energy. By comparing the BAO scale at different points in cosmic history, scientists can determine how the rate of expansion has changed over time. If the universe's expansion were slowing down, the BAO scale would appear differently than it does today. Instead, observations have confirmed that the universe's expansion is speeding up, providing strong evidence for dark energy. BAO measurements are also used to test theories about the topology of the universe. If the universe were finite and wrapped around itself in a toroidal or multi-connected topology, the BAO pattern might show unusual repetitions or alignments. Likewise, if the universe had significant curvature, either spherical or hyperbolic, the expected BAO scale might be slightly different than what is observed. By analyzing BAO signals across large cosmic distances, scientists can refine their understanding of whether the universe is truly flat or if it has a more complex geometry. One of the challenges in using BAO is separating its signal from other cosmic effects. Gravity, dark matter, and even the motions of galaxies introduce variations in clustering that can obscure the pure BAO signature. Scientists rely on statistical methods and computational models to extract the BAO pattern from massive datasets. Advanced simulations help test different cosmological models, ensuring that the observed BAO scale matches theoretical predictions. The Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope will provide even deeper galaxy surveys, capturing faint objects at extreme distances. These projects will allow astronomers to refine BAO measurements with greater precision than ever before. The more accurately we can measure BAO, the better we can determine the true nature of cosmic expansion and the forces shaping the universe. Echoes of the Big Bang, insights from the cosmic microwave background. The cosmic microwave background carries within it crucial information about the universe's structure, composition, and even its overall shape. By studying the tiny variations imprinted in this cosmic radiation, scientists can trace the universe's history and uncover the fundamental nature of space itself. At first, the CMB existed as high-energy light, but as the universe expanded over billions of years, its wavelength stretched due to cosmic expansion, shifting into the microwave region of the electromagnetic spectrum. Today, the CMB is detected as a uniform, faint glow covering the entire sky, with a temperature of just 2.73 Kelvin, barely above absolute zero. It may seem smooth to the naked eye, but detailed measurements reveal tiny fluctuations, small temperature differences that correspond to density variations in the early universe. These fluctuations are crucial because they reveal the first structures in the cosmos, the seeds from which galaxies and clusters eventually formed. Beyond mapping the universe's early structure, the CMB provides one of the most direct ways to determine its overall shape. Just as the geometry of Earth's surface can be inferred by measuring the angles of a large triangle drawn on it, the geometry of the universe can be determined by analyzing patterns in the CMB. So far, detailed studies of the CMB show that these fluctuations appear to match what would be expected in a flat universe. The CMB also provides insight into cosmic inflation. Inflation not only smoothed out irregularities in the early universe, but also stretched space in such a way that, if it had any initial curvature, it was effectively flattened. The temperature fluctuations seen in the CMB are not just random variations, but follow a precise statistical pattern. The specific way in which these fluctuations are arranged allows scientists to probe deeper into the composition of the universe. For example, the presence of dark matter and dark energy can be inferred by analyzing how these temperature variations have evolved over time. Ordinary matter, which makes up stars, planets, and galaxies, accounts for only about 5% of the universe's total energy content. Dark matter makes up roughly 27%, while dark energy dominates at 68%. By examining the polarization of the CMB, the way its light waves are oriented, scientists can also look for subtle signals left behind by gravitational waves from the early universe. These gravitational waves would have been produced during the inflationary period, offering direct evidence of the processes that shape the fabric of space-time. Some experiments, such as BICEP-2, have sought to detect these signals, though initial claims of discovery have been met with challenges, as dust in our own galaxy can create similar effects. One of the most remarkable aspects of the CMB is that it provides a cosmic reference point. No matter where an observer is in the universe, they will see the CMB in nearly the same way, with the same temperature and same patterns of fluctuations. This reinforces the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. However, there are small anomalies in the CMB that have sparked debate. Some studies have suggested that there may be unexpected alignments or asymmetries, such as the so-called axis of evil, a term used to describe an unusual alignment in temperature fluctuations across vast cosmic scales. If real, such patterns could suggest new physics beyond our current models, possibly pointing to large-scale structure in the universe that standard inflationary theory does not predict. The CMB is often referred to as the baby picture of the universe, capturing it in an early stage before stars, galaxies, and planets emerged. But it is more than just a historical relic. It is an active tool that continues to refine our understanding of cosmic topology and fundamental physics. As observational techniques improve, future missions such as CMB-S4 aim to achieve even more precise measurements, searching for deeper insights into inflation, dark matter, and the possible large-scale shape of the universe. Gravitational lensing, nature's own telescope into cosmic shape. At its core, gravitational lensing works much like a magnifying glass, but on a cosmic scale. When light from a distant object, such as a quasar or a galaxy, passes near a massive body on its way to Earth, the gravitational pull of that mass bends the light. This warping effect can cause the background object to appear distorted, stretched, magnified, or even duplicated. This effect has been observed countless times, allowing astronomers to uncover objects and structures that would otherwise remain hidden. There are three main types of gravitational lensing: strong lensing, weak lensing, and microlensing. Strong lensing occurs when the alignment between a distant light source, a massive intervening object, and the observer is nearly perfect. This results in dramatic distortions, such as the formation of multiple images of the same object, arcs, or even an Einstein ring, a perfect circular lensing effect that occurs when the alignment is exact. Some of the most famous examples of strong lensing are seen in deep space images captured by telescopes like Hubble, where entire galaxies are visibly stretched and curved by the gravity of foreground galaxy clusters. Weak lensing, in contrast, involves more subtle distortions that are harder to detect with the naked eye. Instead of clear multiple images, weak lensing causes the shapes of background galaxies to be slightly stretched or sheared. By studying large numbers of galaxies and analyzing these distortions statistically, astronomers can reconstruct maps of the dark matter distribution in the universe. Dark matter's gravitational influence is unmistakable through its lensing effects. Microlensing occurs on a much smaller scale and is used primarily to detect objects that are too dim to observe otherwise. When a single star or planet passes in front of another star, its gravitational pull temporarily amplifies the background star's light. This effect has been used to detect exoplanets, rogue planets drifting through space, and even isolated black holes that would otherwise be invisible. Gravitational lensing is one of the best tools for probing the shape of the universe itself. The way light bends depends on the curvature of space-time, which in turn depends on the total mass and energy content of the universe. If space were curved in a significant way, the lensing patterns we observe would show deviations from what we expect in a flat universe. Large-scale surveys of weak lensing effects, such as those conducted by the Dark Energy Survey and Euclid Space Telescope, are helping to refine our measurements of cosmic curvature, giving us a clearer picture of the universe's overall geometry. One of the most intriguing uses of gravitational lensing is in studying the cosmic web. Galaxies are not randomly scattered, but instead form a vast interconnected network of filaments and voids. These filaments, composed largely of dark matter, act as gravitational highways, guiding the formation of galaxies along their strands. By mapping how light bends across enormous distances, astronomers can trace mass distribution on the largest scales. Gravitational lensing also offers a way to test general relativity. While Einstein's equations have held up under every test so far, extreme conditions, such as those near black holes or in the early universe, could reveal subtle deviations. Some alternative theories of gravity predict different lensing effects, meaning that by analyzing lensing data with ever greater precision, scientists may one day uncover new physics beyond Einstein's theory. Another fascinating application of gravitational lensing is its role as a cosmic time machine. Since light takes time to travel across space, the images we receive from lensed galaxies are not snapshots of their present state, but rather glimpses into their distant past. In some cases, lensing has allowed astronomers to see galaxies as they appeared just a few 100 million years after the Big Bang, offering unprecedented insights into the universe's early history. One of the most famous gravitational lensing discoveries was Icarus, the most distant star ever observed at the time of its discovery in 2018. Normally, individual stars at such distances would be impossible to detect, but Icarus was briefly magnified by the lensing effect of a massive galaxy cluster. Similarly, lensing has been used to detect some of the most ancient galaxies, helping to fill in the missing pieces of cosmic evolution. Through gravitational lensing, nature provides its own telescopes, offering a unique and powerful way to explore the hidden depths of space and map the unseen. Innovative observational techniques beyond traditional astrometry. For centuries, astronomers have relied on traditional astrometry, the precise measurement of the positions and motions of celestial objects, to map the cosmos. While this method has provided invaluable insights, the rapid advancement of technology has opened up entirely new ways of observing and understanding the universe. Emerging observational techniques now go beyond simple position tracking, allowing scientists to probe deeper into cosmic structures, detect objects hidden in the vastness of space, and refine measurements with unprecedented precision. These innovations are revolutionizing modern cosmology and reshaping our understanding of the universe's shape, structure, and evolution. One of the most groundbreaking advancements in astronomy is the rise of interferometry, a technique that combines the signals from multiple telescopes to create a virtual telescope much larger than any single instrument. The Event Horizon Telescope, or EHT, used this method to capture the first ever image of a black hole in 2019. By linking radio telescopes across the globe, the EHT effectively created an Earth-sized observatory, allowing astronomers to resolve details millions of light-years away. This same technique is now being applied to study the structure of the universe on the largest scales. The Square Kilometre Array, set to be the world's largest radio telescope, will use interferometry to create detailed maps of cosmic evolution, revealing how galaxies form and how the large-scale structure of the universe has changed over time. Another revolutionary method is gravitational wave astronomy, which opened an entirely new window into the cosmos. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting ripples in space-time caused by the collision of two black holes. Unlike light-based observations, gravitational waves allow astronomers to study cosmic events that would otherwise remain hidden, such as the mergers of neutron stars and black holes in distant galaxies. Future space-based observatories will expand gravitational wave detection to even lower frequencies, allowing scientists to probe the earliest moments of the universe, potentially uncovering evidence of cosmic inflation or exotic topological defects in space-time. Astronomers are also leveraging advances in adaptive optics, a technology that corrects for the blurring effects of Earth's atmosphere in real time. Ground-based telescopes, such as the Very Large Telescope and the upcoming Extremely Large Telescope, use laser-guide stars to measure atmospheric distortions, enabling them to capture images with clarity that rivals space telescopes. This advancement allows astronomers to study distant galaxies, exoplanets, and cosmic structures with remarkable precision, providing deeper insights into the universe's composition and geometry. Neutrino astronomy is another emerging field. Unlike light, neutrinos can pass through vast stretches of space unimpeded. The IceCube Neutrino Observatory, buried deep within the Antarctic ice, detects these elusive particles as they travel through Earth, offering a unique way to study distant supernovae, gamma-ray bursts, and black hole collisions. Because neutrinos interact so weakly with matter, they provide an unaltered view of the high-energy universe, revealing details that traditional telescopes cannot detect. The development of quantum-based sensors is also pushing the boundaries of observational astronomy. Ultra-precise atomic clocks and quantum interferometers are being designed to detect tiny variations in space-time, potentially uncovering evidence of exotic physics such as dark matter interactions or minute fluctuations in gravitational waves. Some researchers speculate that quantum sensors could even help detect the shape of the universe by measuring minute warps in space-time across cosmic distances. New high-resolution spectrographs, like those on the James Webb Space Telescope, or JWST, allow astronomers to analyze the chemical composition of distant galaxies and planetary atmospheres with incredible detail. By examining how light is absorbed and emitted by different elements, scientists can reconstruct the history of the universe, identifying the earliest structures, and understanding how cosmic expansion affects matter distribution. Time domain astronomy, which focuses on changes in celestial objects over time, is becoming more critical than ever. While traditional astronomy relied on static images of the sky, modern observatories are designed to detect rapid changes, such as supernovae, neutron star collisions, and even fast radio bursts, or FRBs. By monitoring these fleeting events across multiple wavelengths, from radio to X-rays, scientists can gather clues about the universe's underlying structure and behavior. The vast amount of data collected by telescopes and space missions is far beyond what human researchers can analyze manually. AI-driven algorithms can identify patterns in cosmic structures, classify galaxies, and even predict the presence of exoplanets based on subtle variations in star brightness. These technologies are particularly useful for large-scale sky surveys, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, which will generate petabytes of astronomical data each year. AI will be critical in making sense of this information, allowing scientists to detect rare cosmic events and refine measurements of the universe's large-scale topology. All these innovations are fundamentally changing the way we observe the universe, providing deeper and more accurate insights into its structure, history, and ultimate fate. Cosmic inflation and its role in shaping universal geometry. The concept of cosmic inflation was introduced in the 1980s as a way to explain several puzzling aspects of the universe. One of these is the horizon problem, the question of why the universe appears so uniform in all directions. If the universe had expanded at a steady rate since the Big Bang, distant regions of the cosmos should not have had enough time to exchange energy or information, yet the CMB is nearly identical everywhere. Inflation provides a solution by suggesting that all regions of space were once much closer together before being rapidly stretched apart. Another mystery inflation helps explain is the flatness problem, the question of why the universe appears to have a nearly perfect Euclidean geometry. Observations suggest that the large-scale curvature of space is either zero or very close to it. However, in standard Big Bang cosmology, even a slight deviation from flatness in the early universe would have grown over time, leading to a highly curved universe today. Inflation provides an elegant answer. Rapid expansion dilutes any initial curvature, much like how blowing up a balloon causes a small patch on its surface to appear flatter as it expands. This is why, despite local variations in mass and energy, the universe appears so close to being flat on cosmic scales. The inflationary period left behind subtle imprints in the universe. One of the most significant effects of inflation is the generation of tiny quantum fluctuations. At the microscopic scale, empty space is never truly empty. It is filled with quantum fluctuations, random variations in energy that constantly arise and disappear. During inflation, these fluctuations were rapidly stretched to macroscopic scales, seeding the formation of galaxies, clusters, and the vast cosmic web of matter we see today. These fluctuations are preserved as temperature variations in the CMB, which we can measure with extraordinary precision. Modern telescopes have mapped these fluctuations in detail, providing some of the strongest evidence for inflation. The patterns of temperature variations across the sky match what inflation predicts, suggesting that the universe's structure was indeed shaped by quantum processes in the first moments of existence. However, the precise details of inflation remain a subject of active research. Scientists are working to determine what kind of inflationary model best describes our universe and what kind of energy field drove this expansion. One possibility is that inflation was driven by a hypothetical inflaton field, a yet-to-be-discovered energy field that would have dominated the early universe. The inflaton field would have acted as a kind of anti-gravity force, causing space itself to stretch. As the universe expanded, the field would have decayed, transferring its energy into ordinary matter and radiation, leading to the hot and dense state we associate with the Big Bang. The exact nature of this field is unknown, but its effects are still visible in the large-scale geometry of the universe. Another major question is whether inflation ever truly ended everywhere. Some models suggest that while inflation ended in our region of the universe, it did not in others. According to this idea, different parts of the cosmos may have undergone different rates of expansion, giving rise to multiple bubble-like universes with varying physical properties. This concept, known as eternal inflation, suggests that our observable universe may be just one small part of a much larger and more complex cosmic structure. If the universe is perfectly flat, or very close to it, as inflation suggests, then its expansion could continue indefinitely. However, if there are slight variations in curvature that we have yet to detect, they could influence whether the universe will eventually slow down, stop expanding, or even collapse in a future big crunch. In ongoing efforts to test inflation, researchers are searching for one of its most significant predictions: primordial gravitational waves. These are ripples in space-time that would have been generated by inflation itself, carrying information about the conditions of the early universe. Unlike gravitational waves detected from black hole mergers, primordial gravitational waves would have left faint signatures in the polarization patterns of the CMB. The ekpyrotic universe, brain collisions, and alternative origins. In the search for a deeper understanding of the universe's origins, the standard Big Bang model has long been the dominant theory. But despite its success in explaining many features of the universe, the Big Bang model leaves some fundamental questions unanswered. What existed before the Big Bang? Why did the universe begin in such a highly ordered state? And could there be a deeper mechanism behind cosmic expansion? One alternative to the Big Bang is the ekpyrotic universe model, a theory that suggests our cosmos was not born from a singular explosion, but rather from a vast cosmic collision. Unlike the standard model, which starts with an initial singularity, the ekpyrotic theory proposes that our universe emerged from the interaction of higher dimensional structures known as branes, short for membranes. This idea originates from string theory and M-theory. In the ekpyrotic scenario, the universe is part of a higher dimensional space where branes exist like massive flexible sheets. Our observable universe is confined to one of these branes, but there could be others parallel to ours, separated by an extra dimension. According to the theory, two such branes drifted toward each other over an immense period of time. When they finally collided, the enormous energy of the impact was converted into matter and radiation, filling our universe with the energy needed to set the stage for cosmic evolution. This event, rather than an explosive singularity, is what the ekpyrotic model describes as the true beginning of the universe as we know it. This model avoids the need for an initial singularity. In traditional Big Bang cosmology, the equations describing the universe break down when tracing time backward to the first moment, leading to infinite density and temperature. The ekpyrotic theory, however, replaces this singularity with a slow-moving pre-existing state where the branes gradually approach each other. This provides a more natural way to explain the emergence of time and space without requiring an infinitely small and hot beginning. Another key feature is that it offers a different perspective on inflation. The ekpyrotic model achieves a similar effect through the properties of the brane collision itself. As the branes approach, they flatten and create an environment where density fluctuations naturally form, leading to the structures we see today. This suggests that the large-scale uniformity of the universe, which inflationary theory explains by rapid expansion, might instead be the result of interactions between higher dimensional objects. In standard cosmology, time begins at the Big Bang, meaning there is no before. The ekpyrotic universe, however, suggests that time could be cyclical, with branes repeatedly moving apart and coming back together over unimaginable timescales. This cyclic universe model proposes that the cosmos undergoes endless cycles of expansion, cooling, contraction, and collision. Each new collision resets the universe, creating a fresh beginning without the need for a singular origin. If the universe follows this kind of cycle, it changes how we think about the ultimate fate of the cosmos. In the traditional view, the universe will either expand forever or collapse back into a singularity. In a cyclic model, however, the universe would never truly end. It would instead undergo a vast sequence of rebirths, with each cycle shaping the conditions for the next. The ekpyrotic theory is still speculative, but it has sparked interest because it provides possible solutions to several unanswered questions in cosmology. One challenge it faces is how to test it observationally. Unlike the standard inflationary model, which predicts specific patterns in the CMB, the ekpyrotic model suggests a different type of imprint on the universe's large-scale structure. Scientists are searching for unique signatures that could distinguish between the two models, but so far the evidence remains inconclusive. Some versions of the ekpyrotic model suggest that gravity could leak into extra dimensions, potentially leading to subtle deviations in how cosmic structures form. Others propose that primordial gravitational waves, if detected, could help determine whether inflation or brane collisions shaped the universe's early history. One of the most compelling aspects of the theory is that it ties together multiple areas of physics, from string theory to general relativity. It suggests that the universe is not just a four-dimensional spacetime, but part of a far more complex and dynamic higher-dimensional structure. This has led some scientists to explore whether brane collisions could also explain the presence of dark matter and dark energy. If additional dimensions exist, they might interact with our universe in ways we have yet to understand, possibly influencing the expansion rate or the distribution of unseen mass in the cosmos. Journey through non-Euclidean realms. Imagine setting out on a voyage across a universe where space itself is curved. In such a realm, the shortest path between 2 points is no longer a straight line, but a curve that follows the shape of the underlying space. If the universe were shaped like a sphere, traveling in one direction indefinitely would eventually bring you back to where you started, much like circumnavigating the Earth. A more extreme departure from Euclidean intuition is found in hyperbolic geometry. Imagine a vast cosmic landscape where every step you take moves you farther than expected, where space itself seems to grow beneath your feet. This kind of geometry is difficult to visualize because it has no perfect representation in ordinary three-dimensional space. However, it can be mathematically described and even partially modeled using intricate curved surfaces that mimic the way hyperbolic space behaves. In such a universe, the usual rules of perspective would break down. Objects might appear to shrink or stretch in strange ways depending on how they move through space. This effect, though imperceptible on small scales, could shape the large-scale structure of the cosmos. Even more bizarre possibilities arise when we consider geometries beyond 3 dimensions. In higher dimensional spaces, the concepts of up, down, left, and right become inadequate to describe all possible directions. A being moving through a four-dimensional space, for instance, would have access to an additional degree of movement, just as a creature living in two dimensions would struggle to comprehend the concept of height. A massive object like the Sun curves the space around it, causing planets to follow curved paths, an idea completely at odds with the straight-line trajectories of classical Newtonian physics. Black holes represent the most extreme example of this curvature, where space folds in on itself so completely that nothing can escape. The possibility that the universe itself follows a non-Euclidean structure means that even the paths of entire galaxies may be shaped by the warping of space on cosmic scales. To truly appreciate the implications of non-Euclidean geometry, consider the idea of a closed, multiply-connected universe. A traveler moving in a straight line might unknowingly loop back to their starting point from a completely different direction. The study of non-Euclidean realms forces us to confront the limits of human intuition. The rules that seem so obvious in our daily lives are not fundamental truths, but rather approximations that break down under extreme conditions. Fractal universes, infinite reflections in a recursive reality. Fractals are geometric shapes that exhibit self-similarity, meaning their structures look the same, whether observed at large or small scales. Some researchers have proposed that the entire universe, rather than being smooth and continuous, might be shaped by these recursive patterns. On the largest scales, we get the impression of a homogeneous isotropic cosmos. However, when observed at finer detail, a different picture emerges. Clusters of galaxies form enormous filaments and voids, creating a cosmic web. This vast network of filaments is eerily similar to structures found in fractal geometry. If this is true, then zooming in or out on the universe might reveal repeating structures, just as zooming into a fractal like the Mandelbrot set reveals an endless cascade of self-similar patterns. One of the most intriguing aspects of a fractal universe is the idea that this patterning could extend down to even the smallest scales. Just as galaxies form clusters, so too do stars within galaxies, planets around stars, and even atoms within matter. If the universe is fractal, then there may be an infinite nesting of similar structures. Some speculative theories suggest that entire universes could exist within black holes, forming a chain of nested realities where each universe gives birth to new universes inside its singularities. Some models suggest that space-time, rather than being a smooth and continuous fabric, might be fundamentally composed of fractal-like structures. Quantum gravity theories propose that at the smallest possible scales, near the Planck length, space-time might resemble a foamy, chaotic fractal. If true, this would mean that the very foundation of reality follows recursive patterns, shaping everything from subatomic particles to the grand structure of the cosmos. Beyond physics, fractals also appear in theories of consciousness and the structure of information itself. Some researchers speculate that the way the brain processes information might be fractal in nature, with neural connections mirroring patterns seen in nature. Others suggest that even fundamental mathematical truths may follow this logic, with simple rules generating infinitely complex structures. If the universe itself follows these patterns, then the laws of physics may not be simple equations, but rather recursive processes that create an infinitely unfolding reality. Many science fiction stories have imagined universes where the same patterns repeat endlessly, where civilizations exist within larger civilizations, or where exploring deeper into reality only reveals further layers of the same structures. Some stories describe recursive universes where traveling in one direction leads back to the starting point in an infinite loop. Much like zooming in on a fractal reveals the same patterns no matter how far one goes. Others imagine worlds where time itself follows a fractal structure, branching endlessly into new possibilities while still retaining an underlying order. A truly fractal cosmos might be infinite not only in space but also in depth, with structures continuing infinitely downward and upward. This would mean that no matter how much we explore, there would always be deeper levels of complexity waiting to be uncovered. It would also suggest that the universe has no fundamental scale, that the same principles governing the behavior of galaxies might also apply to the tiniest particles. Some studies suggest that large-scale structures exhibit fractal-like behavior up to a certain point, but beyond that, the universe appears to smooth out and become homogeneous. However, others argue that our current observational limits may simply prevent us from seeing the full picture. If the universe is indeed fractal, then it may only be detectable at certain scales, requiring new methods of measurement and analysis to fully reveal its structure. The search for a deeper understanding of the universe often leads back to patterns that have existed all along. Fractals, with their endless complexity and recursive beauty, may provide a clue to the very nature of reality itself. Whether the universe is truly fractal or simply exhibits fractal-like behavior in certain aspects remains an open question. However, the idea inspires both scientific inquiry and philosophical reflection, offering a glimpse into a cosmos that is at once infinitely vast and intimately connected at every level. Dark energy, shaping the cosmic landscape. In a universe without dark energy, gravity would act as the primary force determining how space evolves over time. If there were enough matter and energy, the gravitational pull of galaxies and other cosmic structures could eventually slow down and even reverse expansion, leading to a possible future collapse. If there were too little matter, expansion would continue indefinitely, but at a slower rate. However, what astronomers observe is that the expansion is speeding up. Dark energy appears to act uniformly across space, meaning it doesn't clump together like ordinary matter. Instead, it behaves more like an inherent property of space itself, causing every region of the universe to stretch over time. This means that even as galaxies pull on each other through gravity, dark energy works in the opposite direction, driving them farther apart. The effects of dark energy become more noticeable on cosmic scales, affecting how the overall geometry of the universe evolves. One way scientists describe the possible effects of dark energy is through the concept of the cosmological constant, originally introduced by Albert Einstein in his equations of general relativity. At first, Einstein added this term to his equations to balance out gravity, thinking the universe must be static. When astronomers later discovered that the universe was expanding, he abandoned the idea, calling it his biggest blunder. However, with the discovery of accelerated expansion, the cosmological constant has returned as a leading explanation for dark energy. It suggests that space itself has an energy density that remains constant over time, meaning as the universe expands, the total amount of dark energy increases because there is more space for it to act within. If dark energy is indeed a cosmological constant, it would mean the universe will continue expanding forever, becoming colder and emptier as galaxies move farther apart. Over time, this could lead to a scenario known as the Big Freeze, where galaxies become isolated, stars slowly burn out, and the cosmos becomes a vast, dark void. In this case, the shape of the universe would remain flat or nearly flat, but space itself would continue stretching at an ever-increasing rate. However, another possibility is that dark energy is not a constant, but a dynamic force that changes over time. Some theories suggest that dark energy could weaken or strengthen in the distant future, leading to entirely different outcomes. One dramatic possibility is the Big Rip, in which dark energy becomes so powerful that it eventually tears apart galaxies, stars, planets, and even atoms. If the force accelerating the universe grows stronger over time, there may come a point when not even subatomic particles can remain bound together, ending the universe in a violent disintegration. Another idea is that dark energy could eventually reverse its effect, causing expansion to slow down and collapse back into a big crunch after all. If this were the case, the universe could experience cycles of expansion and contraction, similar to some cyclic universe theories. The flatness of the observable universe is surprising because, in general relativity, the overall shape of space is determined by the total amount of matter and energy it contains. a flat universe requires a specific balance between the gravitational pull of matter and the outward push of dark energy. Observations suggest that dark energy provides the extra energy density needed to keep this balance, explaining why the universe does not appear strongly curved in one direction or another. To study dark energy, astronomers use several observational techniques. One of the most important involves type Ia supernovae, which act as cosmic standard candles for measuring distances. By comparing the brightness of these exploding stars at different points in cosmic history, scientists were able to confirm that the universe's expansion has been accelerating for billions of years. Other methods include baryon acoustic oscillations and gravitational lensing. Despite these advances, the true nature of dark energy remains one of the biggest mysteries in modern physics. Some speculate that it could be related to quantum mechanics, possibly arising from vacuum energy. Others claim that it signals a need for new physics. Could we be inside a black hole? Black holes are some of the most mysterious objects in the universe. They warp space and time in ways that defy normal intuition. While they are typically thought of as compact objects that consume matter, some scientists have proposed a radical idea. What if our entire universe is actually the interior of a black hole? This concept stems from the way black holes bend space-time. From an outside perspective, anything approaching the event horizon appears to slow down, never quite disappearing from view. However, for an observer inside the black hole, space and time behave differently. Instead of falling toward a single point, they might experience an expanding region, one that could, in theory, resemble our universe. If the universe itself were the interior of a black hole, then the event horizon would be an invisible boundary surrounding everything we know. This would mean that everything we observe exists within a four-dimensional hypersphere, a curved space that is contained within the larger structure of a black hole. From the inside, the universe would appear infinite, just as it does to us, but from an external viewpoint, it could be just one of many such regions connected through a larger cosmic framework. One way to explore this idea is by looking at the mathematics of black holes. Physicists have long studied the possibility that black holes do not simply end in singularities, but instead create new regions of space on the other side. In some models, these regions can continue expanding indefinitely, just like our observable universe. This idea aligns with theories that suggest that every black hole might give birth to a new universe, with each event horizon acting as a kind of cosmic gateway to another reality. Another reason this idea is intriguing is that it could help explain the observed geometry of our universe. The universe appears to be nearly flat on large scales, however. In a black hole model, this apparent flatness could be an illusion created by the way space is curved inside the event horizon. We might be experiencing a locally flat universe that is actually curved on a much larger scale. The idea of a universe inside a black hole also connects to the nature of cosmic expansion. If we were inside a black hole, this expansion might be a natural consequence of the way space behaves within the event horizon. The process of gravitational collapse that forms a black hole from the outside could, from the inside, appear as a continuous stretching of space, exactly like what we observe as cosmic inflation and expansion. Some theories suggest that our universe could be the interior of a giant rotating black hole, or a Kerr black hole. Unlike static black holes, these objects have an additional feature called an ergosphere, a region where space itself is dragged along by the black hole's rotation. If our universe exists inside such a structure, it could explain why space-time appears to have a preferred direction of motion on large scales, which some cosmological observations suggest might be the case. One challenge with this idea is that black holes, as we understand them, eventually lose mass through Hawking radiation, a process in which they slowly evaporate over time. If our universe were inside a black hole, this raises the question, what happens when the black hole evaporates? Some physicists speculate that if a black hole's interior can expand indefinitely, then from our perspective, it might continue existing forever, even if the black hole appears to disappear from the outside. Others suggest that the universe might eventually experience a catastrophic end, tied to the fate of the black hole. The idea of being inside a black hole also ties into the holographic principle, a concept in theoretical physics suggesting that all of the information in our universe could be encoded on a distant surface, potentially the event horizon of a black hole. If true, this would mean that everything we perceive as three-dimensional space is actually a projection from a lower dimensional boundary, similar to how a hologram appears to be three-dimensional despite being stored on a two-dimensional surface. Some models take this even further, suggesting that black holes might be fundamental building blocks of the cosmos. In this view, every black hole could spawn its own universe, with the laws of physics in each one slightly different from those in the parent universe. This idea provides a potential mechanism for explaining why our universe has the particular physical constants that allow life to exist. If there are an infinite number of black hole universes, then it is inevitable that at least some of them would have conditions suitable for complex structures to form. If the universe is inside a black hole, it would radically change how we think about the cosmic boundary. Rather than existing in an infinite expanse of space, we might be part of a closed system, with the event horizon acting as an impenetrable limit beyond which nothing can escape. This could explain why we see a finite, observable universe, with no clear indication of what lies beyond its edges. It might also mean that there is an outside reality, one where our universe is just a small region within a much larger, possibly higher dimensional structure. Topological defects, cosmic relics from the universe's early phase transitions. The early universe was a place of extreme conditions, where matter and energy behaved in ways that seem alien compared to what we see today. In those first moments after the Big Bang, temperatures and densities were so high that the fundamental forces of nature were unified, indistinguishable from one another. But as the universe expanded and cooled, these forces separated through a series of phase transitions, much like how water turns to ice as it freezes. These transitions were not always smooth. Sometimes they left behind imperfections, irregularities in the fabric of space itself. These remnants, known as topological defects, are thought to be scars from the universe's earliest moments. Topological defects arise when different regions of space settle into different states during a phase transition, failing to match up perfectly where they meet. This is similar to what happens when a sheet of ice freezes unevenly, leaving behind cracks. The universe, instead of ice, is made up of fields, energy distributions that govern the behavior of fundamental forces and particles. When these fields shift from a high-energy unified state to a lower-energy structured one, defects can form at the boundaries where the new configurations don't align. There are different kinds of topological defects, each with its own characteristics and potential role in shaping cosmic evolution. Some of the most widely studied are monopoles, cosmic strings, domain walls, and textures. Each type represents a different kind of irregularity in how energy fields settled during the early universe's cooling process. Magnetic monopoles were one of the first predicted topological defects. In electromagnetism, we're familiar with the concept that magnets always have two poles, a north and a south. No matter how many times you cut a magnet in half, each piece will always have both poles. However, certain grand unified theories predict that during the early universe's phase transitions, single-pole magnetic objects, monopoles, could have formed. These would be like isolated north or south poles, carrying magnetic charge without an opposite counterpart. Despite being predicted by theory, no monopoles have ever been found, leading scientists to wonder if something about cosmic evolution suppressed their creation, or if they exist but are so rare that they have yet to be detected. Cosmic strings are another possibility. Thin, one-dimensional defects stretching across space like enormous threads. These would have formed if different regions of the universe fell into different states, leaving behind narrow, high-energy boundaries where the transitions didn't line up. Cosmic strings, if they exist, would be incredibly dense, meaning that even a tiny segment of one could weigh as much as a planet. As they move, they would warp the space around them, bending light and affecting the motion of nearby objects. Some researchers have speculated that certain gravitational lensing events could be evidence of cosmic strings slicing through space. Another kind of defect, domain walls, are two-dimensional structures that form when different regions of space settle into distinct but equally possible states. Imagine a vast plane where different sections freeze into slightly different patterns. At the borders where those patterns meet, irregular boundaries appear. Domain walls would have formed in a similar way if the early universe's energy field settled into multiple stable configurations. If these walls had persisted to the present day, they would divide the universe into separate regions, each with slightly different physical properties. However, observational evidence suggests that domain walls, if they ever existed, must have either decayed away or been extremely rare. A more complex type of defect, textures, occurs in situations where the entire universe undergoes shifts in energy states, but the shifts don't align perfectly over large distances. Textures are not as localized as cosmic strings or domain walls. They are more like regions of misalignment that gradually smooth out over time. Unlike other defects, textures don't persist indefinitely. Instead, they decay, releasing energy in the form of radiation. Some scientists have proposed that certain unexplained patterns in the CMB could be linked to ancient textures fading away. While topological defects were once thought to be inevitable consequences of the early universe's evolution, their apparent absence presents a challenge. If defects like monopoles and domain walls should have formed, why haven't we seen them? One possible explanation comes from inflation, which would have stretched space so dramatically that any defects present at that time would have been diluted to near invisibility. If inflation wiped out defects, they may still exist, but at scales so large that they are beyond our current observational reach. Despite their elusive nature, some researchers continue searching for signs of relics from the universe's early phase transitions. If any of these defects were discovered, they would provide crucial insights into high-energy physics, offering a direct link to the conditions that existed in the first moments of cosmic history. Their presence would also help test and refine theories about the fundamental forces, potentially offering clues about how gravity, electromagnetism, and nuclear forces were once unified. Some theories suggest that cosmic strings or other defects might create localized variations in density, acting as seeds for the formation of galaxies. Others propose that defects could influence the large-scale structure of the universe in subtle ways, affecting how galaxies and galaxy clusters are distributed. If these cosmic relics are ever detected, they could reveal traces of the moment when everything we see today was just beginning to take shape. Computational cosmology, simulating complex topologies. Understanding the shape and structure of the universe is a task that stretches beyond what human intuition alone can grasp. The vast scales, the complex interactions between matter and energy, and the subtle distortions of space-time all require sophisticated tools to analyze and predict. This is where computational cosmology becomes essential. By using powerful computers to simulate different cosmic models, scientists can test theories about the shape of the universe, its large-scale structure, and the evolution of galaxies and cosmic filaments. These simulations are detailed mathematical constructions that help compare theoretical predictions with actual observations. At the core of computational cosmology is the need to handle enormous amounts of data. The universe contains billions of galaxies, each with billions of stars, and the gravitational interactions between them unfold over billions of years. Modeling even a small portion of this requires processing power far beyond what even a team of people could calculate. Supercomputers, equipped with thousands of processors, are designed to handle these vast computations, breaking down the universe into a grid of simulated particles that represent matter, energy, and space-time itself. One of the most famous computational efforts in cosmology is the Millennium Simulation, a project designed to model the formation of cosmic structures over time. Running on some of the most advanced supercomputers of its time, it simulated the evolution of a portion of the universe containing over 10 billion particles, each representing a chunk of dark matter. The simulation tracked how these particles interacted under the force of gravity, forming the intricate web of filaments, clusters, and voids that characterize the real universe. The results closely matched observations from telescope surveys. Modern simulations go even further, incorporating additional factors like dark energy and the influence of topological defects that may have formed in the early universe. Some models introduce non-Euclidean geometries to test how alternative shapes affect the observed distribution of galaxies. By adjusting initial conditions, such as the amount of dark matter, the rate of cosmic inflation, or the possibility of extra dimensions, scientists can explore a range of scenarios and compare them against the real universe. One particularly exciting area of computational cosmology is simulating the CMB in different shaped universes. If the universe has a non-trivial topology, light traveling through space might create repeated patterns in the CMB. Simulations allow scientists to model what these patterns should look like for different shapes, such as a toroidal universe or a dodecahedral space. By comparing simulated CMB maps to real ones obtained from telescopes like Planck and WMAP, researchers can look for clues about the universe's true shape. Another key use of simulations is in modeling gravitational lensing. If the universe has a complex topology, light might create duplicate images in the sky. Simulated universes with different curvatures and structures help astronomers understand what patterns to expect in real observations. Neural networks, which mimic the way human brains recognize patterns, are being trained to analyze these vast amounts of simulated data. These AI-driven models can quickly identify patterns in galaxy distributions, detect gravitational lensing effects, and even suggest which cosmological parameters best fit observational data. This allows researchers to explore far more possibilities than would be feasible with traditional methods alone. The future of computational cosmology lies in even more detailed simulations that incorporate quantum effects, exotic particles, and alternative theories of gravity. Some researchers are exploring simulations that go beyond general relativity, testing ideas from quantum gravity and string theory to see how they might affect large-scale cosmic structures. As computing power continues to grow, these models will become more refined, offering an ever clearer picture of how the universe evolved and what its fundamental shape might be. By bridging the gap between theory and observation, computational cosmology allows scientists to explore scenarios that would be impossible to test in a laboratory and to simulate billions of years of cosmic history in a matter of weeks. Topological data analysis. Understanding the large-scale structure of the universe requires advanced mathematical tools to decode the patterns hidden in vast amounts of cosmic data. While traditional methods in cosmology rely on models of gravity, radiation, and particle physics, there is a growing need for techniques that can reveal subtle structures within the data itself. This is where topological data analysis, or TDA, comes into play. By applying concepts from topology, scientists can extract meaningful information from astronomical surveys, simulations, and CMB maps. At its core, TDA is about recognizing patterns in data that may not be immediately obvious. Instead of looking at individual points, such as galaxies or clusters, TDA examines the relationships between them, seeking out hidden structures that persist across different scales. The universe isn't a random scattering of matter. It has a definite structure, forming filaments, walls, and voids that shape its geometry. By using topological techniques, researchers can quantify these features and compare them to theoretical models. One of the key tools in TDA is persistent homology, a method that detects features in data that remain stable across different resolutions. Imagine looking at the cosmic web, which stretches across billions of light years. At one scale, it may appear as a collection of individual points. Zooming out, connections between these points emerge, revealing filaments and clusters. With even more distance, these structures merge into larger cosmic formations. Persistent homology helps track these connections, identifying features that endure across multiple levels of observation. This makes it particularly useful in studying the evolution of the universe's large-scale structure. Large-scale galaxy surveys, such as those conducted by the Sloan Digital Sky Survey, or SDSS, collect vast amounts of data about the positions and motions of galaxies. Traditional methods analyze this data by measuring distances and clustering properties. But TDA offers a different approach. Instead of just counting galaxies in certain regions, it looks at the overall shape of the structures they form. Are there large voids surrounded by filamentary structures? Do these structures connect in a way that suggests a repeating or finite topology? TDA can quantify these questions by detecting loops, holes, and other features in the data that might be invisible to standard statistical approaches. One of the surprising insights gained from applying TDA is the possibility that the universe may have topological defects. If such defects exist, they would be nearly impossible to identify using traditional methods, but TDA provides a framework for detecting unusual shapes or discontinuities in the cosmic fabric. One of the challenges in using TDA for cosmology is interpreting the results. While topological features can be identified mathematically, understanding their physical significance requires careful comparison with theoretical models. Researchers must bridge the gap between abstract mathematical structures and tangible cosmic properties. This is why TDA is often used in conjunction with other methods, such as traditional statistical analyses and direct observations, to ensure that its findings align with our understanding of physics. Anisotropies and irregularities beyond a uniform cosmic expansion. The cosmological principle states that no matter where an observer is located, the universe should look roughly the same in every direction. This assumption has guided much of modern cosmology. However, closer scrutiny of astronomical data reveals that the universe is not perfectly smooth. Small anisotropies, variations in density, temperature, and expansion rate, hint at deeper complexities in the geometry of spacetime. When first observed, the CMB appeared to be nearly uniform in every direction. However, more precise measurements revealed tiny fluctuations, regions of slightly higher and lower temperature. The presence of these irregularities suggests that the universe's expansion was not perfectly even, and studying them provides clues about the underlying geometry and physics of the cosmos. One major discovery in recent years is that some large-scale anomalies in the CMB temperature map don't fit neatly into standard models. For instance, there is a feature known as the CMB cold spot, a region that is significantly cooler than expected. Some scientists propose that this could be the result of a vast underdense region or void in the universe, an area where there is much less matter than in surrounding regions. Others speculate that the cold spot might hint at exotic physics, such as interactions with parallel universes or remnants of cosmic phase transitions from the early universe. Beyond the CMB, anisotropies also appear in the distribution of galaxies. Large-scale surveys, such as the SDSS, have mapped the positions of millions of galaxies, revealing that they are not randomly scattered, but instead form intricate structures. Certain regions appear to be expanding at slightly different rates than others, leading researchers to question whether some fundamental asymmetry exists in the shape or properties of the universe. The Hubble constant, which describes the rate at which galaxies recede due to cosmic expansion, has traditionally been measured under the assumption that this rate is the same everywhere. However, some recent studies suggest that there might be slight directional variations, meaning that the universe is expanding anisotropically rather than uniformly. A related anomaly is the axis of evil, a peculiar alignment of certain CMB fluctuations along a preferred direction in space. This observation has puzzled cosmologists, as it seems to contradict the expectation that the universe has no special direction. Some suggest that this alignment could be due to an unaccounted-for foreground effect, while others entertain the possibility that it reflects a deeper cosmic structure. If the universe has a non-trivial topology, then light and matter could be distributed in ways that produce subtle directional variations. Observing these patterns could provide a direct test of whether the cosmos is finite or infinite in its spatial extent. Exploring hyperbolic space, the universe in negative curvature. In hyperbolic space, parallel lines may diverge from each other instead of remaining equidistant, and the angles of a triangle can add up to less than 180 degrees. If you were to try and draw a perfect square in such a space, you would find that it bends and stretches in unexpected ways. Unlike a spherical universe where space curves back on itself like the surface of a planet, hyperbolic space expands outward infinitely while still maintaining a consistent negative curvature. If the universe has a hyperbolic geometry, it would mean that space is fundamentally curved away from itself at every point. One way to picture this is by imagining a saddle shape, which curves downward in one direction and upward in another. No matter where you are in such a universe, space would always curve outward around you. In a flat space, light moves in straight lines, while in a spherical space, it can curve back on itself, potentially allowing an observer to see the same object from multiple directions. In a hyperbolic universe, light would spread out much more quickly, meaning that distant galaxies might appear smaller than expected because space itself would be stretching them apart in a way that differs from standard expansion. If the universe follows a hyperbolic geometry, then matter should be arranged in a way that reflects this curvature. Some models suggest that galaxies would be distributed in patterns resembling intricate, interwoven webs, a structure that would emerge naturally from the mathematics of hyperbolic space. One of the more unexpected consequences of a hyperbolic universe is that space could be finite yet boundless. This means that the universe might have a limited volume while still lacking any defined edge. If space is hyperbolic, it could wrap around in complex ways, leading to multiple connected paths between 2 points. In such a scenario, if an observer were to travel in a straight line for an extremely long time, they might not return to their starting point, as they would in a spherical universe, but could instead end up in an entirely different location. Mathematicians have explored various tiling patterns that could describe how a hyperbolic universe might be structured. These patterns show how space could be divided into repeating curved shapes that never quite fit together in a way that satisfies Euclidean rules. Some cosmologists have speculated that if the universe has a hyperbolic structure, it might have a repeating pattern at its largest scales, where similar regions of space appear over and over again in different orientations. In a hyperbolic model, dark energy might behave differently, potentially explaining why its effects appear to vary over time. Some researchers have even suggested that the accelerating expansion we observe today could be linked to the underlying curvature of space, rather than an unknown form of energy. Finite versus infinite, the implications of cosmic boundaries. If the universe is truly infinite, it presents some strange possibilities. For one, it would mean that every possible configuration of matter, no matter how improbable, could exist somewhere. This could mean that there are duplicate versions of Earth scattered across the cosmos, where another version of you might be reading these same words right now. While this may sound like science fiction, the mathematics of an infinite universe suggest that it could be true. If the universe were finite, light from distant regions might have wrapped around and interfered with itself, creating patterns in the CMB. So far, observations suggest that space is very close to flat, which would be consistent with an infinite universe. But the possibility of a vast yet finite cosmos remains open. If the universe is finite, does that mean it had a beginning and an end? If it is infinite, does that mean there was no true origin, and that time stretches back eternally? These questions force us to confront ideas that go beyond simple observation and enter the realm of metaphysics. One of the biggest philosophical challenges of an infinite universe is the idea of the multiverse. If space truly extends forever, then it is likely that everything that can happen will happen somewhere. This would mean that not only is our universe infinite, but that there may be infinitely many other universes, each with different physical laws and structures. Some scientists argue that this is an unavoidable consequence of certain models of cosmic inflation. If the universe is finite, does that make existence more special, more unique? If it is infinite, does that mean life, even intelligent life, is inevitable somewhere? Throughout history, humans have often placed themselves at the center of the cosmos, believing that our planet, our galaxy, and our universe are somehow unique. But an infinite cosmos challenges that notion, suggesting that we might be just one small part of an endless, ever-growing expanse. The question of infinity is not just about space. It is also about time. If the universe is truly infinite, does that mean time stretches endlessly into the past and the future? Some models of physics suggest that the universe could be cyclic, meaning that there was no absolute beginning, only an eternal sequence of transformations. The concept of infinity has long been a topic of fascination in both science and philosophy. The ancient Greeks debated whether space could continue forever, or if it had an outer limit. In modern times, mathematicians have explored different sizes of infinity, revealing that some infinities are larger than others. In physics, the idea of infinity often leads to paradoxes and unresolved questions, showing that our understanding of the cosmos is still incomplete. Cosmic symmetry breaking, the impact on universal structure. In the earliest moments of the universe, the cosmos was a place of extraordinary uniformity. Matter and energy were spread out almost evenly, and the fundamental forces of nature were indistinguishable from one another. This high symmetry state did not last long. As the universe expanded and cooled, these symmetries began to break, leading to the formation of the diverse structures and physical laws that govern our reality today. This process, known as cosmic symmetry breaking, was one of the most fundamental events in shaping the universe. It determined how forces interact and why particles have mass. Without symmetry breaking, the universe would be an entirely different place, possibly one where atoms, stars, and galaxies never formed. In physics, symmetry refers to situations where a system remains unchanged under certain transformations. For example, a perfect sphere looks the same from any angle, making it highly symmetrical. But if that sphere is slightly deformed into an irregular shape, the symmetry is lost. This idea applies not just to objects, but to the fundamental forces and particles that make up reality. Scientists believe that, in the extreme conditions of the early universe, the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were initially unified into a single force. This would mean that the universe in its first moments had a much simpler set of physical laws. One of the most important examples of symmetry breaking occurred when the electroweak force, a combination of the electromagnetic force and the weak nuclear force, split into two separate forces. This event is thought to have happened within the first fraction of a second after the Big Bang. The separation of these forces was accompanied by the emergence of the Higgs field, an invisible energy field that gives particles mass. The Higgs boson, discovered in 2012 at CERN's Large Hadron Collider, or LHC, provided direct evidence that this process took place. Without this event, fundamental particles would remain massless, and the universe would lack the stable matter necessary for the formation of atoms, planets, and life itself. If the early universe had remained perfectly symmetrical, matter would have been evenly distributed, creating a featureless, uniform cosmos. But tiny quantum fluctuations were present during the early expansion. When the universe underwent rapid inflation, these fluctuations were stretched across vast distances, eventually forming the seeds of cosmic structures. Areas with slightly more matter attracted even more matter through gravity, leading to the formation of galaxies, stars, and planets. Without this small break in perfect uniformity, the universe would be a far less interesting place. Another consequence of symmetry breaking is the matter-antimatter asymmetry observed in the universe. According to standard physics, the Big Bang should have created equal amounts of matter and antimatter. If that had happened, every particle of matter would have annihilated with its antimatter counterpart, leaving behind only radiation. However, for reasons that remain a mystery, a slight imbalance occurred. For every billion antimatter particles, there were about 1,000,000,001 matter particles. This tiny excess was enough to ensure that some matter survived, eventually forming all the galaxies, stars, and planets that exist today. Scientists believe that symmetry breaking played a key role in creating this imbalance, although the exact mechanism remains one of the biggest unsolved mysteries in physics. Even today, symmetry breaking remains a central concept in physics, shaping our understanding of forces, particles, and the evolution of the cosmos. Scientists use particle accelerators, like the Large Hadron Collider, to recreate the high-energy conditions that existed in the early universe, allowing them to study how symmetries behave under extreme conditions. These experiments help physicists refine their theories about the origins of the universe and the fundamental nature of reality. Higher dimensional spaces, beyond the familiar 3 dimensions. The idea of extra dimensions first gained serious attention in the early 20th century. In 1919, the mathematician Theodore Kaluza proposed an extension to general relativity. Kaluza suggested that by adding a 5th dimension, the equations of relativity naturally included Maxwell's equations, which describe electromagnetism. This was a startling realization. It hinted that gravity and electromagnetism, 2 of nature's fundamental forces, might be linked through an unseen higher dimension. A decade later, physicist Oscar Klein expanded on this idea, suggesting that the extra dimension might be compactified, meaning that it is curled up into an incredibly small scale, far beyond our ability to detect directly. This concept of compactified dimensions remains central to modern theories that propose higher dimensional spaces. String theory requires extra dimensions to function. The most common versions of string theory suggest that space has 10 dimensions, 9 of space and 1 of time. These extra dimensions are thought to be curled up at scales much smaller than the atom. Some theories propose that the universe itself might have a higher dimensional structure. This brain-world scenario suggests that our entire universe exists within a higher dimensional reality, much like a sheet of paper floating in a larger 3-dimensional space. If this is true, there could be entire other universes just beyond our reach, separated from us by an extra-dimensional gap. Though these ideas are fascinating, detecting extra dimensions is extremely challenging. Because they are thought to be hidden at tiny scales, they cannot be seen with ordinary microscopes or telescopes. Instead, physicists look for indirect evidence. One approach involves studying the effects of gravity at very small distances. If gravity does extend into extra dimensions, it could behave differently than expected at extremely short ranges. Experiments are being conducted using precise measurements of gravitational forces on microscopic scales to search for any deviations that might indicate the presence of extra dimensions. Another potential test comes from high-energy physics experiments, such as those conducted at the LHC. If extra dimensions exist, they might reveal themselves in particle collisions. Some theories predict that when particles collide at high speeds, they could produce microscopic black holes, tiny, short-lived objects that form and decay almost instantly. The appearance of such black holes would be a strong hint that extra dimensions are real, since they would require extra spatial directions for particles to collapse into. Beyond physics, the idea of higher dimensional spaces has influenced other fields, including mathematics and even philosophy. In mathematics, higher dimensions are studied using abstract geometry, where spaces of 4, 5, or even infinite dimensions are explored through equations rather than physical intuition. These mathematical ideas help physicists develop theories about what higher dimensional space might be like, even if we cannot directly see it. In philosophy, the existence of extra dimensions raises questions about perception and reality. If humans are 3-dimensional beings living in a higher dimensional universe, What aspects of reality might we be completely unaware of? Could there be entire worlds that exist just beyond our ability to detect them? Observational challenges. Distilling signal from cosmic noise. Astronomy relies on light, but the universe is not a pristine laboratory. Every observation is a battle against noise. Unwanted signals that obscure the data scientists seek. The cosmos is filled with interfering sources, both natural and artificial, making it a challenge to extract meaningful information from the vast amounts of raw data collected by telescopes and detectors. Understanding the fundamental shape of the universe, its contents, and its evolution all depend on how well researchers can filter out noise while preserving the underlying signals that reveal cosmic truths. One of the most persistent challenges in astronomical observations comes from Earth's own atmosphere. Ground-based telescopes must contend with atmospheric turbulence, the same effect that makes stars twinkle when viewed from the surface. This turbulence distorts light as it travels through different layers of air, creating a constantly shifting image. To counteract this, modern observatories use adaptive optics, systems that rapidly adjust mirrors in real time to correct for atmospheric disturbances. By doing so, astronomers can produce much sharper images, approaching the quality of those taken from space. However, even space telescopes face their own set of challenges. Instruments like the JWST must operate in extreme environments, far from Earth's interference, but they still encounter background radiation, stray cosmic rays, and even the faint heat of the telescope itself. Shielding, careful sensor calibration, and sophisticated data processing techniques are essential to minimize these effects and ensure that the recorded signals truly represent distant astronomical objects rather than instrument noise. A major difficulty in studying the large-scale structure of the universe is the presence of foreground contamination. For example, when mapping the CMB, astronomers must remove interference from our own galaxy. The Milky Way is filled with dust and charged particles that emit radiation, blending into the signal astronomers are trying to isolate. Specialized techniques, such as multi-frequency analysis, allow researchers to separate the microwave background from these foreground sources by observing the sky at different wavelengths and identifying distinct spectral fingerprints. Another source of observational noise comes from gravitational lensing. While lensing is often useful in astronomy, it also distorts images in complex ways. When light from far-off sources bends around massive objects, the result is a stretched and warped view of the universe. Scientists must carefully model these distortions to reconstruct the true appearance of celestial objects. Cosmic rays, high-energy particles originating from deep space, can strike telescopes and detectors, creating false signals that must be filtered out. Space-based observatories are particularly vulnerable, as they lack the protective barrier of Earth's atmosphere. Engineers design instruments with shielding and error detection algorithms to reduce the impact of cosmic rays, but some contamination is inevitable. Data scientists must process vast amounts of information to distinguish genuine astrophysical events from these random bursts of energy. Radio astronomy faces a unique problem: human-made interference. Many of the signals astronomers study, such as emissions from distant galaxies or pulsars, exist at the same radio frequencies used by satellites, communication networks, and even household devices. Radio telescopes, like those used in the search for extraterrestrial intelligence, or SETI, must filter out this artificial noise to avoid mistaking human-made signals for cosmic phenomena. Some observatories are built in radio quiet zones, remote areas where electronic interference is strictly controlled. But even these precautions do not eliminate the challenge entirely. In addition to noise from the environment, the very process of data collection introduces errors. Telescopes and sensors have limitations, including sensitivity thresholds, instrumental biases, and calibration issues. Every measurement contains some degree of uncertainty, and astronomers must apply statistical techniques to determine how much of what they see is real and how much is a product of instrument imperfections. Cross-checking data from multiple observatories helps verify results, reducing the likelihood of mistaking noise for a true signal. Novel laboratory experiments, simulating cosmic conditions on Earth. By recreating aspects of the universe under controlled conditions, researchers can test theories, refine models, and observe processes that would otherwise be impossible to study in real time. These novel laboratory experiments allow for deeper insights into cosmic events, from the behavior of black holes to the early universe's extreme temperatures and pressures. One of the most remarkable areas of laboratory astrophysics involves recreating the conditions of the early universe. Particle accelerators, like those at CERN, can briefly mimic those conditions by colliding particles at nearly the speed of light. These collisions generate temperatures millions of times hotter than the Sun's core, briefly creating quark-gluon plasma, the same ultra-hot, fundamental state of matter that filled the universe in its first microseconds. By studying this plasma, scientists can learn how particles interacted before atoms formed, shedding light on the fundamental forces that shaped cosmic evolution. Another major focus of laboratory experiments is recreating the behavior of high-energy astrophysical phenomena. Black holes are some of the most mysterious objects in the universe, and direct observation is often limited to detecting their gravitational influence or radiation from their surroundings. However, physicists have found ways to simulate some aspects of black holes in the lab. Using ultra-cold atoms, researchers have created analog black holes, where sound waves, instead of light, become trapped in a region mimicking an event horizon. These experiments provide insights into Hawking radiation. If laboratory black holes reveal new details about this radiation, it could provide clues about the ultimate fate of real black holes in space. The universe is threaded with vast magnetic fields, influencing the motion of charged particles, shaping galaxies, and even playing a role in the formation of stars. Yet the origins of these cosmic fields remain a mystery. Some of the most powerful magnetic fields are found around neutron stars and pulsars, where forces are so extreme they can accelerate particles to nearly the speed of light. In a laboratory setting, scientists use high-intensity lasers to generate extreme magnetic fields in miniature, studying how plasma behaves under conditions resembling those found in neutron star atmospheres. These experiments help unravel how cosmic magnetic fields influence astrophysical structures over time. Understanding cosmic explosions, such as supernovae, has also benefited from controlled experiments. Supernovae occur when massive stars reach the end of their lives, collapsing and then explosively releasing energy that can outshine an entire galaxy. The shock waves from these explosions drive the formation of new stars, disperse heavy elements, and shape the interstellar medium. However, supernovae happen over thousands or millions of light years and take place over months or years, making direct study difficult. To simulate these processes, scientists use high-powered lasers to generate tiny, superheated plasmas that mimic the behavior of supernova shock waves. These experiments allow for detailed observations of how energy moves through a medium, helping researchers refine models of real supernovae. Earth's atmosphere constantly absorbs cosmic rays, but their origins and behavior in deep space remain an open question. Particle accelerators can simulate these high-energy interactions, allowing scientists to test how cosmic rays interact with matter. These experiments provide insight into high-energy astrophysical events, such as gamma-ray bursts, and the environments around black holes, where such particles are generated. Since dark matter does not emit, absorb, or reflect light, it remains invisible to telescopes. However, underground laboratories, shielded from cosmic rays and other background noise, are designed to detect the rare and faint interactions that dark matter particles might have with ordinary matter. Highly sensitive detectors, often placed in deep mines or inside mountains, look for tiny signals that could confirm dark matter's existence. While no direct detection has yet been made, These experiments continue to push the boundaries of what is possible, refining our understanding of one of the greatest mysteries in cosmology. Some features of the universe, such as galaxy formation and large-scale cosmic flows, can be modeled using carefully designed fluid experiments on Earth. For example, rotating tanks of fluid can be used to study turbulence and vortices, which mirror the large-scale motion of interstellar gas clouds. These insights help explain how galaxies evolve over billions of years and how matter clumps together to form the structures we see today. Some of the most puzzling aspects of the universe, such as the behavior of matter near black holes or in neutron stars, require quantum mechanical descriptions. By using specialized quantum systems, such as ultra-cold atoms or superconducting circuits, researchers can create laboratory analogues of these extreme conditions. Quantum simulations also provide new ways to test theories about gravity, relativity, and exotic states of matter that exist under extreme cosmic conditions. Future missions and technologies. New windows into cosmic topology. Over the centuries, the evolution of telescopes, satellites, and computational tools has steadily pushed the boundaries of what can be seen and understood. Today, astronomers stand on the threshold of a new era, with upcoming space missions and advanced technologies promising to revolutionize how we study cosmic topology. These next-generation instruments will not only refine existing measurements, but could also reveal unexpected aspects of the universe's shape, offering deeper insights into its geometry, expansion, and hidden features. One of the most anticipated missions in the coming years is the Nancy Grace Roman Space Telescope. Named after the scientist who helped establish modern space-based astronomy, this telescope is set to become one of the most powerful tools for investigating the large-scale structure of the universe. Roman's wide-field instrument will provide a panoramic view of the cosmos, capturing images with a field of view 100 times larger than that of the Hubble Space Telescope. This means it will be able to map the distribution of galaxies with unprecedented detail, helping scientists trace how cosmic structures formed and evolved over time. By studying the precise distribution of galaxies, researchers can gain new insights into whether the universe's shape aligns more with a flat, curved, or hyperbolic model. Another key player in this next wave of discovery is the European Space Agency's Euclid mission. Launched with the goal of mapping the universe's dark components, Euclid will measure the large-scale structure of galaxies and study the way light bends due to gravitational lensing. By analyzing these distortions, scientists can infer how mass is distributed throughout the cosmos, including the effects of dark matter and dark energy. The shape of the universe is deeply tied to these invisible forces, and Euclid's precise measurements will help refine our understanding of cosmic topology. Spread across 2 continents, South Africa and Australia, the square-kilometre array is a vast network of radio telescopes that will be one of the most sensitive instruments ever built. Its ability to detect faint radio signals from the early universe will allow scientists to map the cosmic web with unparalleled accuracy. Certain topological features, such as repeating patterns or unexpected symmetries, could potentially emerge in SKA's data. The Laser Interferometer Space Antenna, or LISA, a future mission planned by the European Space Agency, will be the first space-based observatory dedicated to detecting gravitational waves. Unlike ground-based detectors, which are limited by Earth's atmosphere and vibrations, LISA will operate in space, allowing it to observe gravitational waves with much greater sensitivity. If gravitational waves show signs of unexpected distortions or echoes from regions beyond our observable universe, they might hint at the presence of extra dimensions or topological features hidden in the fabric of spacetime. The IceCube Neutrino Observatory has already detected high-energy neutrinos, but future detectors will be even more powerful. Proposed facilities like IceCube Gen 2 will expand our ability to track neutrino sources, potentially offering a new way to map cosmic structures and test whether the distribution of mass aligns with current models of a flat or curved universe. The Planck satellite provided some of the most precise measurements of the CMB, but future missions like the proposed CMB-S4 experiment will push the limits even further. By measuring temperature fluctuations with greater accuracy, scientists can more precisely define whether the universe exhibits subtle curvature or if it is perfectly flat on cosmic scales. Proposed experiments using quantum entanglement and interferometry could test whether space has an underlying discrete structure rather than being a smooth continuum. If space-time itself has a hidden geometric complexity, it could reshape our understanding of cosmic topology in ways currently unimaginable. With these upcoming missions and technologies, the next few decades promise to be a golden age for unraveling the shape of the universe. As instruments grow more sensitive and data analysis becomes more sophisticated, the possibility of discovering unexpected topological features becomes increasingly likely. Wormholes and portals, speculative gateways in a curved cosmos. Wormholes, often described as bridges through space and time, emerge naturally from general relativity. The mathematics of curved space-time suggests that under the right conditions, two distant points could be connected through a tunnel-like structure. If such a passage existed, it could theoretically allow instant travel across vast cosmic distances, bypassing the need for slow, conventional movement through space. A massive object like a planet or a star bends the space around it, creating what we perceive as gravitational attraction. In theory, if two such regions were connected, a tunnel could form between them. This tunnel, a wormhole, could link separate locations in the universe, or even different points in time. The idea gained serious attention in 1935, when physicists Albert Einstein and Nathan Rosen proposed what is now called the Einstein-Rosen bridge. Their work suggested that black holes might not just be destructive objects that consume everything in their path, but could also serve as gateways. However, these bridges appeared unstable. Any attempt to cross one would likely result in its immediate collapse. Later studies expanded on this, exploring whether exotic forms of matter, substances with negative energy, could hold a wormhole open long enough for something to pass through. The problem is that no known form of regular matter or energy behaves in the way needed to stabilize a traversable wormhole. Exotic matter, if it exists, would need to exert a kind of anti-gravitational force, counteracting the natural tendency of the tunnel to collapse under its own weight. Some speculative theories suggest that quantum effects might allow for such materials, but there is currently no experimental evidence to confirm their existence. If the universe allows such structures, could they serve as natural highways across the cosmos? Might advanced civilizations have found a way to create or harness them? The search for such phenomena has led physicists to explore alternative interpretations of cosmic structure. Some theories suggest that wormholes might serve as connections between entirely different universes, linking parallel realities in a vast cosmic web. In this view, what appears to be empty space could be hiding corridors between worlds. A wormhole might not only take a traveler across the galaxy, but could lead to a universe with completely different physical laws. One of the biggest questions surrounding wormholes is whether they could be artificially created. If an advanced civilization had access to the right kind of energy and technology, could they manufacture a stable wormhole? The energy requirements would be extreme, possibly rivaling the total output of an entire star. But if the laws of physics permit such a structure, then a sufficiently advanced society might eventually develop the means to construct one. A wormhole's mouth might appear like a black hole from a distance, since both involve regions of highly curved spacetime. However, unlike a black hole, a traversable wormhole wouldn't have an event horizon. Some theorists have proposed searching for lensing effects that don't match what we'd expect from a normal black hole. Some researchers have examined gamma-ray bursts and unusual gravitational lensing patterns for hints of their existence. So far, no definitive signs have been found, but the possibility remains open. If a wormhole were discovered, It would revolutionize our understanding of the universe and open the door to new questions about the nature of space, time, and travel. And with that, our journey comes to an end. Leave a comment on what other aspect of our mind-bending universe you'd love to learn more of. If you enjoyed this voyage, consider leaving a like and subscribing to the channel. Thanks for watching.